In this video, we're going to take a look at some more end behavior examples for rational functions. Determining end behavior is really just a result of using polynomial division. So when your end behavior approaches an actual number, such as in our last example in the last video, it was at 0, then the rational function has a horizontal asymptote at its end behavior. And we saw as we zoomed out more and more, our example resembled the line y equals 0, which was the horizontal asymptote. So we're going to get a horizontal asymptote under a couple conditions. First of all, if the degree of the numerator is less than the degree of the denominator, so the bigger degree is on the bottom, that's going to give you the x-axis or a horizontal asymptote of y equals 0. If the degree of the numerator equals the degree of the denominator, then the horizontal asymptote will just be nothing more than a ratio of the leading coefficients. So if the smaller degree is on top, your horizontal asymptote is y equals 0. It's the x-axis, much like the numerical example we saw in the last video. And if your degree of your numerator is equal to your degree of your denominator, then just look at the ratio of leading coefficients. On the other hand, if the degree of the numerator is larger than the degree of the denominator, so the bigger degree is on top, the end behavior is not going to be a horizontal line, which we know horizontal lines are just flat lines. They don't have any tilt at all to them. Instead, you're going to have an oblique or a slant asymptote. So for those ones, you're going to need to use polynomial division to find the equation of the oblique asymptote. So example 2, let's determine the end behavior for each and then find the equation of the asymptote. So we have f of x is 5x over x squared plus 1. Our degree of our numerator is 1. Our degree of our denominator is 2. The degree of the numerator is smaller than the degree of the denominator. So because our degree on top is smaller than our degree on the bottom, we have a horizontal asymptote at y equals 0, or the x-axis. And if we take a look at the graph of example 2a, here's our graph. If we zoom out more and more, notice that it looks just like the horizontal line y equals 0. In fact, if we go out pretty far, we might even get the, well, there we go, over 10,000. It doesn't have enough space to store the decimal, so it just gives you back a 0 in return. Hit on home. All right. So if we use polynomial division for our problem, x squared plus 1 does not go into 5x at all, so we have 0. The remainder is the function itself. And as we saw in the first video where we listed out the tables where we had x going up to, let's say, 1,000,000, this is going to approach, this 5x over x squared plus 1 is going to approach 0 the further that x goes towards infinity or negative infinity. So we have 0 plus 0 is 0. So using polynomial division, we still get the same answer anyway. All right, part B, we have g of x equals x squared minus 4 over x plus 1. Here our degree of our numerator is larger than our degree of our denominator. So we do not have a horizontal asymptote, we have an oblique asymptote. And to get that oblique asymptote, we're going to have to use some polynomial division. So we have x squared plus 0x minus 4. Don't forget about filling in that missing 0x term, divided by x plus 1. So we'll start with the x squared. X squared divided by x, we'll put that answer up in this first column is x, and then x times 1 is just x. This x plus this value must equal 0, so this value in the upper right square has to be negative x. And then negative x divided by x is negative 1, and negative 1 times 1 is negative 1. So we've got accounted for the x squared. When we combine these two terms, we've accounted for the 0. We have not accounted for the negative 4. So what do we have to add to negative 1 to get negative 4? We have to add negative 3. So writing this answer out, like we did with dividing polynomials, we get x minus 1 minus 3 over x plus 1. And if we take a look at what the graph of x squared minus 4 over x plus 1 looks like, here's the graph of our function x squared minus 4 over x plus 1. And as we zoom out more and more, notice we get a line here going further to the left and further to the right that looks to be at about an angle. So it would appear as if it's a line like y equals x, where our slope is 1 and our y-intercept is 0. But let's just be safe and take a look. So we have our slant asymptote is x minus 1 minus 3 over x plus 1. So with the slant asymptote or the oblique asymptote, don't worry about the remainder part. That's not going to have any impact. Worry about the quotient part. So x minus 1, because the further out we go, this 3 over x minus 1 is going to get closer and closer to 0. So we'll just have x minus 1 and then minus 0 is just x minus 1. And if we graph y equals x minus 1, we can see it covers that up pretty nicely. But as we go further out, notice how our graph is getting closer and closer in green to that oblique asymptote in purple, the x minus 1. All right, part C, we have h of x equals 6x cubed minus 3x plus 1 over 5 minus 2x cubed. Our degree of our numerator, if we switch our denominator around and write it in standard form, we'll put the negative 2x cubed first. Now our degree of our numerator and our degree of our denominator are both 3, so they're equal. So we look at the lead coefficients. We will have a horizontal asymptote. 6 divided by negative 2 is negative 3, and that's our horizontal asymptote, y equals negative 3. If we look at, didn't mean to do that. If we look at our graph in example 2c, and I'll just graph y equals negative 3, negative 3. Well, my bad, we'll hide that there. As we zoom out, see a little bit of space here, but as we zoom out, the further out we go, if we go way out here, we get negative 3 in return the further out we go. So without having to actually plug in something like x equals 10,000, we can get our end behavior fairly easily. So if we perform polynomial division with 6x cubed minus 3x plus 1 over negative 2x cubed plus 5, we get negative 3, and then our remainder is negative 3x plus 16. But with rational functions, the remainder doesn't have an impact. The further out we go, the less of an impact it has. So our horizontal asymptote is negative 3 plus essentially 0, which is negative 3. So, all right, that about does it for this video. Thanks for watching. I'll see you next time.